So Katie Knowles is a final year PhD student in the Solar and Space Physics group at Northumbria University. She's currently writing up her thesis and has a postdoc position lined up in a few months' time. Congratulations.
Thank you.
Her research aims to shed light on the extent to which Jupiter's non-auroral ionosphere is driven by the powerful magnetic field and turbulent lower atmosphere, and to observationally constrain how such coupling influences its structure, variability, and energetics using Earth and space-based telescopes, which she'll expand on in much more detail imminently. Thanks for joining us, Katie, and when you're ready, please take it away.
Ian, thank you very much for the introduction and the invitation to speak today. Apologies again that you're just looking at a picture, but it is a pleasure to be presenting our analysis today on the auroral footprints of Jupiter's Galilean moons as spotted by the James Webb Space Telescope. So the very broad focus of this talk will be a little bit different from the previous one. We'll be talking today about our solar system's largest planet, the gas giant Jupiter. And by observing Jupiter across a multitude of wavelengths, each wavelength range reveals unique information on the system. So at infrared wavelengths, you are sensing the deep thermal glows from the lower atmosphere, whereas the ultraviolet or UV, it reveals Jupiter's spectacular northern and southern lights, for example. But today we will be discussing near infrared measurements of Jupiter, which allows you to sense the outermost component of Jupiter's atmosphere, known as its upper atmosphere. Now, an upper atmosphere is defined as when the turbulent mixing or eddy diffusion within the lower atmosphere no longer dominates, such that each atom and molecule can separate according to its weight under gravity, essentially meaning different constituents will dominate the population at different altitudes depending on their scale height. So this makes the upper atmospheres of the giant planets extremely low density and therefore highly sensitive to any inputs from above and below. They consist of two co-located regions, a neutral thermosphere, which is composed primarily of molecular hydrogen, and a charged ionosphere, which contains the dominant molecular ion H3+, which we'll be hearing a lot about today. So H3 plus was first discovered by none other than J.J. Thomson back in 1911 and then was detected within Jupiter's upper atmosphere some 78 years later. Now, to create H3 plus, you need lots of molecular hydrogen, which we just said is abundant within the thermospheres of our giant planets. But you also require a source of ionization, and that could be either solar photons on the dayside planetary disk or through energetic particle precipitation about the magnetic poles, creating the beautiful aurora. Once formed, H3 plus is a fantastic emitter at near infrared wavelengths. So using telescopes like JWST, we can measure the intensity of its unique emission lines to see the morphology of the ionosphere's near infrared emissions. By taking the ratio of its spectral lines, we can also infer its temperature. And since H3 plus is thermalized to the surrounding neutral atmosphere, if you measure the temperature of H3 plus, you have a measure of the temperature of the local region of the thermosphere, allowing us to investigate heating processes like auroral Joule heating, for example. We can also determine the H3 plus column density, which essentially tells you in a given region how much H3 plus is being created or destroyed. So it acts as a tracer of molecular hydrogen ionization rates or energy inputs into the upper atmosphere. And lastly, by combining the H3 plus temperature and column density, we can derive something known as its total emission, which represents a measure of the amount of energy lost by the upper atmosphere through H3 plus's thermal emissions. So I'm now going to briefly introduce the aspect of Jupiter's upper atmosphere that we aim to elucidate using H3 plus. So for that, we begin at Jupiter's spectacular northern lights, shown here at ultraviolet wavelengths. These are the brightest and most continuously observable planetary aurora within the entire solar system. And the striking auroral feature that we will be investigating today are the emissions induced by Jupiter's Galilean satellites. They have no counterpart at Earth and are known as the auroral footprints. I'll hopefully explain what I mean by that now with this slide. So I initially want you to focus on the figure on the left-hand side of the screen. So I welcome you to the inner space environment surrounding Jupiter, or the inner magnetosphere. And we can see three of Jupiter's largest moons, the Galilean moons, starting off with Io, which is the closest to the planet, sitting at 5.9 Jupiter radii away from Jupiter. We then have Europa sitting at 9.4 Jupiter radii away, and even further out, we then have Ganymede. Now, those turquoise lines you can see on the screen depict magnetic field lines, which you can see originate from the planet. Now, Jupiter is an incredibly fast rotator. It has a rotation rate of about 11 hours, and those magnetic field lines rotate with the planet. The Galilean moons, however, orbit Jupiter much more slowly. So they continuously interact with those magnetic field lines and the magnetospheric plasma that they carry with it. And that moon magnetosphere interaction leads to the generation of Alfvén waves, which are oscillations along magnetic field lines that can accelerate plasma along the fields, and they eventually crash into Jupiter's upper atmosphere and cause it to glow at the feet of the magnetic field lines that connect Jupiter to the environment close to and downstream of the moons. So if we go back to our picture of Jupiter's aurora, these auroral footprints appear as a bright spot of emission, followed by a fading tail of emission. And I'll highlight Io's auroral footprint on the screen now. They are observable across both infrared and ultraviolet wavelengths, and each one magnetically traces back to its corresponding moon. So because Io is the innermost Galilean moon, its auroral footprint occurs the most equatorward. Now, the auroral footprints of Jupiter's Galilean moons have been measured previously, providing sporadic snapshots of their complexity in the emissions alone. We are currently severely lacking spectral information, such as the H3 plus temperatures and column densities that I mentioned earlier. But what can H3 plus actually tell us about the auroral footprint? So as a reminder, spectroscopic analysis of H3 plus provides measurements on the physical parameters of the ionosphere. The ionosphere is what couples the planet to that surrounding space environment. It is this thin, charged boundary layer that sits at the top of the atmosphere and is what mediates the exchanges between the lower atmosphere and the magnetosphere. So in terms of the auroral footprints, H3 plus measurements allow us to gain insights on the Galilean moons and their local plasma environments, because it provides details on how the footprints are generated. For example, why are the auroral footprints bright at near infrared wavelengths? Is it because of an increase in the local H3 plus temperature or an increase in the local ion density? We can also place constraints on the precipitating particles, as the flux of the incoming electrons will directly affect the amount of H3 plus that is created. And the energy of those electrons will influence the altitude at which H3 plus is produced within the ionosphere. For example, higher energy electrons are able to punch down to deeper layers of the atmosphere where it is cooler. But the ultimate question that people love to ask is, why should we care? Well, firstly, I kind of gave you a clue. We can infer information on the moons, their local plasma environments, and their interaction with Jupiter's magnetic field by taking measurements of Jupiter, which I think is kind of crazy. We can learn about the moons without looking at them. And this is going to be really useful context because there are two missions currently on their way to the Jovian system, JWST and Europa Clipper, who are going to be directly investigating these Galilean moons. So we can provide context before, during, and after the timing of those missions. Secondly, auroral footprints occur elsewhere. The moon Enceladus creates an auroral footprint on Saturn, and there are also linked phenomena within exoplanet systems or even brown dwarfs. Lastly, as much as it pains me to say this, Jupiter is not unique. Around a third of exoplanets that are discovered are Jupiter-like. So the more we learn about Jupiter and the Jovian system, our closest natural lab, the more we can apply that knowledge to within our solar system and then further afar. So hopefully now I've somewhat set the scene and convinced you all to care about H3 plus. Let's actually dive into the details of this study. So the James Webb Space Telescope conducted a clockwise scan of observations around Jupiter's entire limb, the entire edge of the planet. 36 observations were taken in total, each separated by 10 degrees in latitude, to give us this 360-degree view around the entire edge of the planet. Now, each one of those 36 observations is actually composed of 4 dithers. These are just small, precise movements made by the telescope, each with an exposure time of 86 seconds. Now, JWST's near-infrared spectrograph, or NIRSpec, has this integral field unit, which provides us with 3-dimensional data cubes with 2 spatial dimensions, so your X, your Y, and then that third dimension is wavelength, our spectral information, allowing us to capture bright H3 plus emission lines between 3 and 5 microns, which we can fit using the amazing open source Python module HEPI. So out of those 144 dithers we had in total, we captured the auroral footprints of both Io and Europa in 5 of them. So I'm now showing you the derived H3 plus emissions for those 5 JWST dithers, where we are progressing further poleward from dither 1 on the left through to dither 5 on the right. We observed the Io footprint across all 5 dithers, and we were able to resolve some of its substructure, including the main alpha and wing spot, which is this bright spot of emission I'm highlighting now, which marks the direct electromagnetic interaction between Io and the magnetosphere. We also were able to resolve the footprint tail, which magnetically traces back to the wake behind Io as it orbits around Jupiter. For Europa, we observed it across dithers 3 to 5, which as shown by the purple arrows. However, due to the northern aurora rotating into view, we're unable to resolve any sort of substructure for the Europa footprint. It just kind of appears as this minor enhancement in the H3 plus emissions. So please believe me when I say that that is the Europa footprint. So I'm now showing you the derived H3 plus temperatures for the 5 JWST dithers, and I wish to draw your attention to dither 3 in the center, where we have identified a spatially confined cold structure that we've never seen before. It is unique to dither 3 and is localized to the very core of the Io main alpha and wing spot. This cold core of H3 plus possesses temperatures of around 540 Kelvin, which are the kind of temperatures we would expect to see at Jupiter's equator, not this close to the hot, bright northern aurora. It is also haloed by 200 Kelvin hotter temperatures, which partially extend into the footprint tail. And we explored a number of different hypotheses for this temperature structure, but determined that the likely driver is a variability in the incident electron energy. You have higher energy electrons precipitating into the core and are therefore able to penetrate deeper down and produce H3 plus at lower altitudes where it is cooler, with H3 plus production occurring at higher, warmer altitudes surrounding it. Moving on, I'm now showing you the corresponding H3 plus column densities for the 5 dithers, where we see significant variability both within and across dithers. And once again, I would like to draw your attention to dither 3, in particular the Io main alpha and wing spot, because the ion densities that we derive are exceptionally high, higher than for any other dither, 3 times larger than what we see in the aurora, and are the highest H3 plus column densities we've ever recorded. And interestingly, the timing difference between dithers 3 and 4, for example, is just 3.5 minutes, yet their H3 plus conditions vary significantly. In dither 3, we observe this highly dense, cold core of H3 plus in the Io main alpha and wing spot. 3.5 minutes later, evidence of that H3 plus population has all but disappeared. This implies that the H3 plus is relatively short-lived at that location. And it led me to the question of, if the H3 plus physical conditions between subsequent dithers are so different, is what is driving their enhanced near-infrared emissions similar? So to answer this question, we isolated a region containing the Io main alpha and wing spot, in this case for dither 2, where we do not observe a high-density cold core of H3 plus. I plot the H3 plus temperature as a function of the brightness, and then calculate a Pearson correlation coefficient denoted by P in the figure. And then I do the same for the H3 plus column density versus the brightness. And what we find is that the increased H3 plus emissions at the Io main alpha and wing spot are primarily driven by an enhancement in the ion density, possessing a Pearson correlation coefficient of 0.87, which kind of makes sense. It glows brightly because there's more stuff there. Around half an hour later in dither 3, however, the Io main alpha and wing spot is painting a similar yet different picture. We once again observe that the H3 plus column densities and the brightness are well correlated. However, an anti-correlation has now been introduced between the temperature and brightness, which once again reveals the two-dimensional structure of the main alpha and wing spot. We observe a bright, dense core of H3 plus that is produced at lower, cooler altitudes, surrounded by H3 plus sitting at higher, warmer altitudes. Notably as well, the column densities across the isolated main alpha and wing spot spatially vary by a factor of 45, which I think is quite incredible, which implies extreme variability in the production of H3 plus that is most likely driven by short-term changes in the flux of the electrons precipitating into the ionosphere. We can also conduct the same analysis for the Europa footprint, in this case in dither 3. And we see that, similar to Io, the enhanced near-infrared emissions at the Europa footprint are driven by an increase in the H3 plus column density. However, there is a distinct outlier to that relationship, which I'm now highlighting. This outlier possesses H3 plus that is relatively bright, dense, yet cool, similar to what we have observed for the Io footprint. But as you can see, this is based on a single data point with relatively large uncertainties, so it's currently statistically challenging to conduct any further analysis with our current observations, but interesting nonetheless. So to summarize, we have presented the first ever measurements of ionospheric H3 plus emissions, temperatures, and ion densities for the auroral footprints of both Io and Europa. We have revealed that their enhanced near-infrared emissions are primarily driven by an increase in the local H3 plus column density, which has not been observed directly until now. Furthermore, we have detected significant variability across Io's main alpha and wing spot in both the H3 plus temperatures, but much more extremely in the densities. And we believe that this is likely due to temporal variations in both the flux and energy of the incident electrons, perhaps due to either local changes within the acceleration process or in the moon magnetosphere interaction itself. However, we cannot currently decipher the specific mechanism responsible for these short-term changes or determine if this represents the typical variability of Io's auroral footprint. Our observations represent just single snapshots in both time and space. So we are currently, across this month, actively taking observations of Jupiter using NASA's Infrared Telescope facility, which is based on Mauna Kea in Hawaii. We are repeatedly scanning Jupiter's northern auroral region across each night, similar to what you can see here on the right-hand side, because we're trying to map the Io footprint as it rotates with the planet. And by repeating this over the course of a month, we can build up a picture of how the Io footprint is modified, not just in time and in space as the planet rotates, but also under varying ionospheric and magnetospheric conditions, which I think is quite exciting. And the bottom scan that you can see here on the right-hand side is actually one of the observations that we took last week. So thank you very much for your attention. I welcome any questions that you may have now. This work is currently under review with geophysical research letters, so if you are interested and would like to learn more, hopefully you can read about it shortly. Thank you again.